and let's talk a little bit about solutions. So in this chapter, we're going to be talking about the properties and calculations involving solutions that we handle in chemistry. So first and foremost, let's define and recall our definition of a solution. A solution is a mixture where one or more pure substances are dissolved in one or more other pure substances. The solute is known as the minor component of the solution. It's the species dissolved in another component. So the aqueous symbol is a big signpost that we have a solute at play, because aqueous state symbols indicate that the species is dissolved in water. So for example, NaCl aqueous is sodium chloride dissolved in water. So sodium chloride in this case would be the solute. The solvent is the major component of the solution. Okay, so if we're drawing like a picture, if we're drawing a pictorial representation of solute and solvent, so let's suppose we have a block of solid sodium chloride, and we have a beaker that contains water. So water would be our solvent, and sodium chloride would be our solute. So if we mix these together, we get a solution of aqueous sodium chloride, where we have sodium chloride dissolved in water. Okay, so now that we have the major terms that we use to discuss solutions established, let's now move on and let's talk about key properties of solutions. So first, solutions have variable composition depending on the amount of solute and solvent added. Okay, they have uniform properties throughout the solution, and the solute can be separated from the solvent via physical means. There's no chemical bonding between solute and solvent. It's purely, you can separate solute and solvent via physical means. Now, if you change the amount of solute with a fixed amount of solvent, you can change the concentration of the solution. Okay? So just to show an example of this, so let's suppose we have our baseline cup containing water, and we add varying amounts of our dye. Okay? So let's suppose in this first example, we add 0.1 grams of dye. And then in terms of our solvent, let's keep this a fixed 0.5, or let's do 0.25 liters, just to show. Okay. Now, if we increase the amount of solute that we add, let's suppose we add 0.2 grams in the same volume of solvent. As we can clearly see, the more solute that we add, the darker and the more opaque the solution color becomes. So as you can see, we can add different amounts of solute to generate solutions with different concentrations. And we can clearly see the difference in solution concentration as the solution with a greater amount of solute, in this case, has a much darker, more pronounced color. So the key takeaway that I want you to know from this discussion is that solutions have variable composition based on the amount of solute and solvent. Depending on your solute to solvent ratio, your solution will have a different concentration or a different amount of solute per amount of solvent. Now, we can also change the amount of solvent. So if you change the amount of solvent with a fixed amount of solute, you observe a change in the concentration of the solution. So let's suppose in this example, we have a fixed amount. So we have a fixed solute mass. So to each of these solutions, we're going to add 0.5 grams of our dye. Just an arbitrary number. And what we're going to do is we're going to have a variable amount of solvent. We're going to use a varying volume of water. Okay? So to each of these samples, we have 0.5 grams of dye. In our most dilute case, we have this in 0.25 liters. In the second case, we have it in 0.125 liters. And in the third case, we have it in 0.0675 liters. So, as we can see, changing the volume of solvent for a fixed amount of solute, for a fixed mass of solute, generates solutions with varying concentrations. So, depending on the amount of solute and solvent, you can get more or less concentrated solutions. So a critical feature of this entire discussion is we need to be very specific on how much solute we're adding and how much solvent we're using to dissolve that solute. Any questions so far on this example? If not, let's keep going. So let's try to visualize a picture of how ionic and covalent compounds dissolve. So let's first look at dissolving an ionic solid. So when you're dissolving an ionic solid, your ions are separated and surrounded by the solvent. So let's just draw a picture. So let's suppose we have some sodium chloride. So let me draw out some sodium chloride. Sodium chloride is an ionic compound that consists of cations and anions. It's not going to be a perfect illustration, but the main feature of ionic compounds is that they contain charged cations and anions. Okay, now we're in water. We're in water right now. So what's going to happen is that water is going to associate with our attempt to disassociate with our cations and anions. So these water molecules will bump into our ionic compound. So our water molecule will bump into our ionic solid. Let me just show that. So this water molecule is just going to bump into our ionic solid, and when water gets close enough to interact with our ions, you're going to observe what is known as an ion dipole interaction between water and your ions. And this water molecule is going to be able to pull this sodium ion or this chloride ion away from the ionic lattice. So it's almost like we're taking apart our ionic solid and placing the ions into solution step by step, almost like taking apart a Lego kit. So by the end of this process, we have our cations, and in this case, our cations are going to be surrounded by water molecules. The oxygen end of water will point towards sodium because oxygen is electron rich. While for our anion, chloride, the hydrogen end of water will point towards chloride. Now, you may say, what is the point of this discussion? Well, the key feature, yep, hydrogens have a delta positive. Yep, they're electron deficient, and this partial positive charge in our dipole interacts with our negatively charged chloride ion. Now, the real point of this discussion is that sodium chloride solid, when it dissolves and you generate sodium chloride aqueous, we can really think of sodium chloride aqueous as sodium plus aqueous and Cl minus aqueous. So just remember, soluble ionic compounds dissociate into their ions in solution. So when you think about aqueous sodium chloride, you really should think, oh, I have ions in solution rather than a whole compound stuck together in solution. Okay. So let's talk next about molecular compounds. So for a molecular compound, your molecules are just surrounded by the solvent. So let's draw a picture once again. And let's pretend that we are trying to dissolve some acetic acid. Actually, yeah, acetic acid would be fine. So initially, our molecules are pretty closely packed. Okay, and now, as always, if we try to dissolve our acetic acid, in water, our water molecules are going to immediately associate with our acetic acid molecules. So again, just like before, the dissolving process is based on proximity and collisions. Your water molecules bump into your acetic acid, and then your water molecules and acetic acid begin to engage in interactions. So water interacts with your acetic acid. And just like in our ionic compound, these water molecules are going to begin to pull your solute into solution and then surround your solute with water molecules. So by the end of this process, we have our acetic acid, and it's going to be surrounded a little more strategically in this case with water molecules. And of course, we'd have multiple molecules of acetic acid that are dissolved in water. Okay, now, the main takeaway from this discussion is this idea that we went from acetic acid in the liquid, acetic acid as a liquid, to aqueous acetic acid. And I'd like you to answer the following question. In this picture that we've drawn, does acetic acid exist as whole molecules or ions primarily? Does acetic acid exist as whole molecules or ions primarily? So looking at the picture, we see exactly whole molecules. So our takeaway from this is when molecular compounds dissolve, whole molecules are present, dissolved in solution. So a big error that I see students make is they start to pick apart their molecular compounds into their pieces, thinking they're an ionic compound. Molecular compounds generally stay together as whole molecules when they dissolve. And we'll leverage these ideas later on in this chapter and in our discussion of ionic and net ionic equations. Okay, so let's talk about factors that affect dissolving ionic and covalent compounds and influence solubility. So solubility can be defined as the maximum amount of solute that will dissolve in a given amount of solvent under a given set of conditions, typically temperature, pressure, etc. Okay. Oh, sure. Perfect. So the first major property that affects solubility are solvent properties, such as like dissolves like. So ionic compounds and polar substances dissolve in polar solvents, such as water. We'll talk more about how to define polar substances later on in this class. We see intuitively, for example, that in our day-to-day lives, so we take, for example, sodium chloride, aqueous, which is clearly an ionic sodium chloride solid, and we try to dissolve it in water. So if we try to dissolve it in water, we have no issue dissolving our sodium chloride in water. And that in turn gives us a nice homogeneous solution of aqueous sodium chloride. Likewise, if we take a polar molecule such as, for example, methanol. So this is a polar molecule, and we try to dissolve it in water. We will, in fact, generate a nice, clear, homogeneous solution of aqueous methanol. Like dissolves like. Polar dissolves polar. Okay. Now, nonpolar substances dissolve in nonpolar solvents. So some common nonpolar solvents that we'll see consist primarily of carbon and hydrogen only. And these nonpolar solvents include C6H6, which is known as benzene, C6H14, which is known as hexanes, C6H12, which is cyclohexane. Essentially, if it has only carbon and hydrogen, then you can consider it a nonpolar solvent. Now, the key point I want to make here is that nonpolar substances dissolve in nonpolar solvents. So, for example, if I have some C6H12 liquid, so let's suppose I have some cyclohexane as a liquid, I can very easily dissolve my cyclohexane, which is very greasy, very nonpolar, in a solution of benzene. Like dissolves like. Nonpolar dissolves nonpolar. Now, we don't use the aqueous symbol if it's dissolved in something other than water. We just say C6H12 liquid in C6H6 liquid. Like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Just to anchor this in some of your intuitive reasoning, obviously oil and water don't mix because you have a polar substance, water, and a nonpolar substance, oil. Like dissolves like. Okay. So another factor that greatly affects solubility is temperature. So as the temperature increases, collisions between the solute and solvent occur more frequently, and the solubility of solids increases with increasing temperature. So the way that we can rationalize this is at low temperatures. For example, if you have your solid and you have your water molecules, based on the temperature, your water molecules will collide and move about with a different relative velocity. So the higher the temperature, the faster your water molecules are moving, and the more collisions you get. So if we compare this low temperature to our high temperature example, the main distinction is that in our high temperature example, we will observe very clearly that more water molecules are impacting our solid, interacting with and trying to dissolve our solid, and they're hitting our solid and engaging in these dissolving interactions at a higher relative velocity. So at high temperature, we have more collisions and more interactions, leading to more solid dissolved. Solubility is built on these intermolecular interactions. If there's not a collision, if the water molecule and your solute are not in close proximity, it takes a lot longer for the dissolving process to occur. So if we were to show an end result, if we compare low temperature to high temperature, we'd see at the end of our low temperature run, say we have a little bit less solute. Well, at the end of our high temperature run, we'd have just a very small amount. So at the end of our high temperature run, we have more solute dissolved. Does this make sense to everyone so far? Intuitively, we know that if, for example, you want to increase the amount of sugar dissolved in your tea, or if you want to increase the amount of honey in your tea, you can just increase the temperature, heat up your drink, and the honey or sugar will dissolve. Now, an interesting feature of gases is that the solubility of gases decreases with increasing temperature. So if we compare, for example, a low temperature trial and let's pretend for our solute, we're looking at oxygen. That's quite a relevant example if you happen to be a fish, or if you're ever curious why, when on a particularly warm day, you may sometimes see the fish start to jump out of the pond. There's a reason for that, and it has to do with the amount of oxygen dissolved. So at low temperatures, we have a large amount of gas dissolved. And as we increase the temperature, the amount of gas that is present outside of the solution increases compared to the amount of gas that is dissolved in solution. Now, this exact phenomena, the explanation behind it, requires a little more information in our chapter on thermochemistry, and it requires a bit of a discussion on entropy in order to fully understand why this phenomena is occurring. The best way that I like to think about it, is that at higher temperatures, it's more favorable for your gas molecules to be present outside of solution, to be present in the relatively disordered gas phase. Because when it's dissolved in solution, you have all these water molecules interacting with your gas molecules. And these interactions, although they're very stabilizing, they are not favorable at higher temperatures, as your gas molecules will substantially prefer, instead of being ordered and surrounded by water molecules, to be in this disordered state where they're in the free gas phase. What I want you to know from this section, what I want you to know from this discussion, is that gas solubility, the amount of gas dissolves, decreases with increasing temperature. So another example of this, so in this first case, we see the amount of oxygen dissolved in water decreases at high temperatures. So for example, if you happen to be a goldfish and you're swimming in a low temperature solution, you have no problems whatsoever. But if you increase the temperature, suddenly there's not as much oxygen and the fish begins to jump out of the water as it can't get enough oxygen. Another example is that warm soda. If you ever tried to drink warm soda is very flat as it has less dissolved carbon dioxide gas. So these are some tangible examples of these phenomena. Does this make sense so far? Can we at least rationalize these ideas based on what we've seen in the world around us? Is it making sense so far? If there aren't any questions, let's talk about the next idea, which is this idea that the solubility of gases increases with increasing pressure. So let's look at a sample. So at low pressure, so let's pretend we have a piston. Okay, so we have a piston. Okay, and then we have some water. And then floating in the gas phase above our liquid is going to be some carbon dioxide gas. Okay. Now, the carbon dioxide can dissolve in water, or it can sit above the solution in the gas phase. So your carbon dioxide molecules are constantly leaving to the gas phase and entering the solution. Now, fundamentally, what's occurring in this process is your carbon dioxide molecules are hitting the solution. They're bouncing around and they're hitting the solution. Okay? And at low pressures, there's plenty of space for your carbon dioxide molecules to bounce around. There's plenty of space for your carbon dioxide molecules to sit in the gas phase. However, as we go to high pressure, let's suppose we push down on our piston and we reduce the available volume. Well, now we begin to see that our carbon dioxide doesn't have a lot of space left. So what's going to happen when we reduce the available volume is that now your carbon dioxide has less space to work with and it collides with the surface of your liquid more readily. So as a result, we have more carbon dioxide dissolved in our solution. So at high pressures, we have more collisions with our solvent, and that in turn leads to more gas dissolved. Fundamentally, solubility is based on these interactions between solute and solvent. At high pressures, your carbon dioxide has less space present above your solution, and as a result, it collides with, interacts with, and dissolves in your solvent more readily. The only thing I want you to know, at high pressure, we have more gas dissolved. We'll explain more about why this works in later chapters. Just as a side note, the solubility of solids and liquids does not change substantially with increasing pressure. Okay, so that was our overview of factors that affect solubility. Let's now drill down a little bit into this idea of different types of solutions. What types of solutions can we have? How do we describe solutions? And What are their properties? So a concentrated solution contains a large amount of solute relative to the maximum dissolvable amount. Okay, so to give an example of this, so let's suppose we have 1 liter of water, and let's suppose our maximum solubility at 25 degrees Celsius was 200 grams per 1 liter. And let's suppose we take our solute, which is dye, and we take 180 grams of dye and we dissolve it in our water. Well, we'd have a pretty concentrated solution and we'd be able to see that right away. And the way that we'd be able to see that is the fact that this concentrated solution would be quite dark. We'd see this very clear red color as we have a concentrated solution. We have 180 grams per 1 liter, and that's very close to your maximum solubility. Okay, let's talk about the other type of solution. A dilute solution contains a small amount of solute relative to the maximum dissolvable amount. So let's pretend this time our maximum solubility at 25 degrees Celsius is 200 grams per 1 liter. And let's start this process over one more time. And let's suppose we have 1 liter of water, except this time we're only going to dissolve a tiny amount. Just let's suppose 20 grams of dye to prepare our solution. So that in turn gives us a dilute solution. So we have 20 grams per 1 liter. And you'd be able to very clearly see if your solute is colored that you have a dilute solution by virtue of the fact that the color will be substantially lighter. So we have 20 grams per 1 liter. It's much less than our maximum solubility. So we have what's considered a dilute solution. Okay. Now, this is redundant since we often see this as the majority of the solutions that we cover in this class, but an aqueous solution has water as the solvent, okay? So for example, CH3OH aqueous, this is methanol dissolved in water. We can also call this an aqueous solution of methanol. Okay, now a non-aqueous solution, water is not the solvent. So an example of this would be C6H6, liquid dissolved in hexane, C6H14. So this is a non-aqueous solvent, and overall, this is a non-aqueous solution. Does this make sense to everyone so far? Any questions so far? If not, let's keep going talking about solutions. Now, there are special terms related to solubility, and we designate solutions as either saturated, unsaturated, or supersaturated. So in a saturated solution, we have the maximum amount of solute dissolved for that temperature and pressure. So let's suppose our maximum solubility is, let's just do 500 grams per 1 liter at 25 degrees Celsius. Okay? We have to specify the temperature because solubility is temperature dependent. So let's designate this the maximum solubility of sodium chloride. And let's suppose we want to make a saturated solution. So to do that, we'd take 500 grams of sodium chloride and we'd very carefully dissolve it in 1 liter of water. That in turn would give us a saturated solution. So the solution would be homogeneous and it would be completely saturated where we have 500 grams of sodium chloride per 1 liter. Okay, now if we try to add, let's suppose we try to add 10 grams of sodium chloride. Let's suppose that we tried to add 10 grams of sodium chloride. That 10 grams will not dissolve. So the key feature of saturated solutions is that excess solute does not dissolve. The solution already has the maximum amount of solute present at that temperature. Okay. Now let's look at the next case, which is an unsaturated solution, which contains less than the maximum amount of solute dissolved. So again, let's consider our max solubility at 25 degrees Celsius is 500 grams per 1 liter. Okay. Now, suppose instead of dissolving 500 grams of sodium chloride, we just dissolve 50 grams of sodium chloride in 1 liter of water. That in turn would give us an unsaturated solution. As we only have 50 grams per 1 liter. Now, the main feature and the main way you can tell that you have an unsaturated solution is that let's suppose we want to add an additional 50 grams of sodium chloride. If we add some additional sodium chloride, what we'll very clearly see is that additional solute will dissolve. Because we still have an additional capacity to dissolve and hold solute in our solvent. We have not yet reached a saturated solution. Does that make sense to everyone so far? The maximum solubility will be noted in the literature. So it'll be always be given to you, and there are actually tables and figures called solubility curves. And we'll actually talk about those solubility curves momentarily. But that's a very good question. How do you determine the maximum solubility? It's often given via solubility curves. Okay, So the last type of solution is quite interesting and requires very careful preparation. These are known as supersaturated solutions, and they contain more than the maximum amount of solute dissolved for that temperature and pressure. Often these solutions require careful heating and cooling, and supersaturated solutions are unstable and solid will precipitate out of the solution when they're agitated. So again, let's suppose our max solubility is 500 grams per 1 liter at 25 degrees Celsius. And let's suppose that we have a solution where we have 600 grams per 1 liter at 30 degrees Celsius. So we've changed the temperature. Okay, so we have a lot of solute dissolved. Now we allow our solution to cool, and we've done something that seems a bit counterintuitive at first glance. We now have a solution where we have 500 grams per 1 liter at 25 degrees Celsius. This is known as supersaturated. Now, the interesting thing about a supersaturated solution is that if you try to add additional solute, what will happen, let me write this up here so there's more space. What will happen when you add additional solute is that instead of just refusing to dissolve, what you will see is that your excess solute will precipitate out. And you'll be left with, at the end of this process, a saturated solution with a large amount of excess solute precipitated. So right here, this is our excess solute precipitates out. So all of this solid that we're now suddenly seeing was dissolved in solution, We had excess solute dissolved in solution. Addition of a little bit more solute causes the solution to precipitate out, to kick out all of its extra solute, and we're left with a saturated solution where we have 500 grams per 1 liter, and we have our remaining excess solid precipitated out. Does this make sense to everyone? So supersaturated solutions have excess solute dissolved. If they're disturbed or if you try to add additional solute, these unstable solutions will precipitate out, will kick out the excess solute to give a saturated solution and their excess solute as a precipitate. Does this idea make sense to everyone? Any questions on this example? If not, there are some questions concerning, well, how do we determine the maximum solubility? That is found by looking at what are known as solubility curves. Well, solubility curves indicate the solubility at different temperatures. They can also indicate the solubility at different pressures, but the most common solubility curves look at temperature. Now, let's read our units carefully. Our units for solubility are grams of solute per 100 grams of water. Whenever you look at a solubility curve, it's important to check the units. Yes. So to answer the question in the chat on supersaturated solutions, just going back to the figure, yes. So anything that can dissolve within the maximum capacity, within your maximum solubility to make a saturated solution, will dissolve at that temperature and pressure. Any additional solute added will not dissolve. You can only dissolve solute up to the solubility limit for that temperature and pressure, assuming you're keeping your temperature and pressure constant. Yep, that's exact. Your statement in the chat is exactly right. Did that address your question? Perfect. Okay, so first we noted the units are grams of solute per 100 grams of water. So each of these curves show the solubility as a function of temperature. So let's do some examples where we read solubility curves. So we're asked to find the solubility of a saturated solution of ammonium nitrate at 20 degrees Celsius. So there are three regions of a solubility curve. So if we're above the line, we have a supersaturated solution. If we are exactly on the line, so if we are on the line, we have a saturated. And if we are below the line, so below the line, we have an unsaturated solution. Okay. So then, looking through this problem, we're looking for a saturated solution of ammonium nitrate. So I find ammonium nitrate, I find 20 degrees Celsius, and I trace my line up until it intersects the ammonium nitrate line spot on. So if we're right on the line, that is known as a saturated solution. Let me use a slightly different color than red so it doesn't make things too confusing. So we trace from 20 degrees Celsius up to our ammonium nitrate line, and then we trace across, and that in turn gives us approximately 175 grams per 100 grams. So we read from our temperature going straight to our solubility curve line, and then we trace across and extrapolate to our solubility on our y-axis. So that in turn gives us a solubility of approximately 175 grams per 100 grams of water. And this, to be specific, is grams of ammonium nitrate. Does this make sense to everyone so far? Does this make sense to everyone so far? Okay, so let's look at another type of problem involving solubility curves. And we're asked, is a solution of 100 grams of sodium hydroxide and 1,000 grams of water saturated, unsaturated, or supersaturated? Okay, so we're asked to figure out, is this solubility above or below the line? Okay, so I'm going to write out my units. I have 100 grams of sodium hydroxide for every 1,000 grams of water. Okay, now remember how I said pay attention to the units? What are the units in this graph? What are the exact units for our solubility? And let's be really specific here, because this is where we need to be very careful. What are the units? for solubility. Yeah, it's grams of solute per 100 grams of water. So then we need to write this as grams of sodium hydroxide per 100 grams of water. So to do that, we're simply going to divide our top and bottom by 10, and that gives us 10 grams of sodium hydroxide per 100 grams of water. Now we're going to go and we're going to find sodium hydroxide. We're going to go from 10 grams. So this point right here is about 10 grams per 100 grams of water. We're going to trace across to 25 degrees Celsius. Okay, so we found 25 degrees Celsius. And comparing to our solubility curve for sodium hydroxide, are we above or below the solubility curve line? Are we above or below the solubility curve line? We're below. So what do we call those solutions where we have less than the maximum amount of dissolved solvent? Where we have less, what do we call those solutions? Saturated, unsaturated, or supersaturated? If we have less than the maximum amount, what do we call that? What type of solutions do we call that? Unsaturated, exactly right. So this solution is unsaturated. Does this make sense to everyone so far? Any questions so far? Okay, so let's now apply what we've learned to the following example. I've given you the same solubility curve. The maximum solubility for different salts. So each of these different compounds have a unique curve, and the maximum solubility at the temperature is the solubility on the line at that temperature. So if you want to find the maximum solubility of a specific salt, you'll have to find the solubility curve or solubility data for that salt. Does that make sense? Perfect. So let's try to apply what we've learned to the following two problem-solving sessions. You're going to need to refer to the solubility curve found in the note set. And I'd like you to answer the question first. What is the solubility of a saturated solution of sodium hydroxide at 25 degrees Celsius? And then is a solution of 300 grams of sodium bromide in 400 grams of water saturated, unsaturated, or supersaturated? So we'll give everyone about 4 to 5 minutes to work through this example, and then we'll come together as a group to discuss. And don't be shy to submit your responses in the chat or via Canvas through Canvas Quiz 5.5. And I'll be checking everyone's progress, and if you have any questions, don't be shy to submit your questions in the chat or unmute and ask your question verbally. And we'll discuss in about 3 to 4 minutes. And it's good, we already have some responses via via Canvas. That's good. Let's try to get more responses via Canvas and in the chat, and then we'll discuss momentarily. And if you want to share your proposed solutions, don't be shy to type them in the chat so we can discuss. And the responses I see in the chat look perfect so far. Let's try to get a few more responses. So far, the responses I see look quite good. And we'll discuss in about another 2 minutes. And checking the chat in Canvas, I see a lot of reasonable responses so far. So now that we have almost the entirety of the class giving responses, let's now discuss these examples. So what is the solubility of a saturated solution of sodium hydroxide at 25 degrees Celsius? So we find 25 degrees Celsius and then we trace up on our line. Then we trace across and we see that this is about 110. Depending on the number of tick marks and the precision associated with your y-axis, you may be able to report more sig figs. But 110 grams of sodium hydroxide per 100 grams of water is a reasonable assignment for the maximum solubility. Does this make sense to everyone so far? Any questions so far? If not, let's look at this next example. We have a solution of 300 grams of sodium bromide in 400 grams of water, okay? But again, we need to be very attentive of the fact that our solubility curve graph is in terms of grams of solute per 100 grams of water. So then, we're going to need to divide both our top and bottom of our ratio by 4. Okay, so let's do that. So we're going to take 300 over 4, and that in turn gives us 75 grams of sodium bromide per 100 grams of water. Okay, now that we have our solubility, we go up to our graph, and let's do this in purple so that way there's some variant. So 75 is somewhere around, so at 25, so we're going to trace up. I'm just going to erase this because they're both at 25. Okay, and 75 is somewhere around here. It's very close. Less close than it looks. Okay, so tracing down to 25, our solubility compared to our solubility curve, is it above or below the line? Are we above or below our maximum solubility? Are we above or below our maximum solubility? We're below, exactly. And so what do we call this solution? Saturated, unsaturated, or supersaturated? What do we call this solution? Saturated, unsaturated, or supersaturated? What do we call a solution where we have less than the maximum amount? We'd call it unsaturated. Perfect. Good, good. Any questions on this example? Any questions on this example? If not, let's continue on now. And let's talk about different measures of solution concentration. So, percent concentration, one common way that percent concentration is expressed is percent by mass, where percent by mass for solutions is defined as the mass of the solute over the mass of the solution times 100%. You can think about percent by mass as the grams of solute per 100 grams of solution. Again, very similar to the logic that we used for mass percent. It's the exact same idea. Now, just as a side note, the mass of the solution is equal to the mass of the solute plus the mass of the solvent. Now, how can we use this for calculations? Well, let's do an example. So in this problem, we're asked, what is the percent by mass, percent m over m? Note, it's unitless because the units cancel. We're asked to find the percent by mass concentration of sucrose in a solution made by dissolving 7.6 grams of sucrose in 83.4 grams of water. Okay, so I'm just gonna label my units. The mass of my solute is 7.6 grams of sucrose. The mass of my solution, whoops, let's start with solvent. Let's do this step by step. The mass of the solvent is 83.4 grams. And as a result, the mass of our solution would be the mass of our solute plus the mass of our solvent, which gives us 91.0 grams. So then, calculating the mass percent, we take the grams of solute over the grams of solution times 100%. And if we punch that into our calculator, let's just punch that into our calculator. We get a mass percent of 8.4%. Rounded to 2 sig figs because our input has 2 sig figs. Does this make sense to everyone so far? Does this make sense to everyone so far? Okay, so let's try to apply what we've learned and let's try to calculate the percent by mass of a new solution. And let's take about 3 minutes to work through this example. And you can submit your responses in the chat verbally, or if you want, you can submit your responses for class polling via Canvas Quiz 5.6. So let's spend about 3 minutes working through this problem, and then we'll come together as a group to discuss. And if you have any questions, don't be shy to type them in the chat or unmute and ask your questions verbally. And we'll discuss in about 3 minutes. And the responses I see in the chat look pretty good so far. And checking the responses so far, I see a number of reasonable responses via Canvas and the chat. Let's try to get a few more responses, and we'll discuss in about another minute and a half. Okay, so let's now discuss this example. So first and foremost, reading through this problem, the mass of our solute, in this case formaldehyde, is 5.0 grams. The mass of our solvent, in this case, is 70.0 grams. Ergo, the mass of our solution is 5.0 grams plus 70.0 grams, which gives us 75.0 grams. Ergo, the mass percent of formaldehyde, which is our solute, is equal to 5.0 grams over 75.0 grams times 100%. Okay, and that in turn gives us a mass percent of 6.7%. Perfect. Any questions on this example? Okay, so let's now look at the next type of problem where we have to use mass over mass percent. So in this example, we're asked how many grams of sucrose must be added to 375 grams of water to prepare a 2.75% mass over mass solution? Well, first let's define our terms. So the mass of solute, which is sucrose, we don't know. So I'm going to put it as X, a variable that we're going to solve for. The mass of solvent in this case is water, which is 375 grams. Okay, and we know that our mass percent is equal to X, which is the grams of sucrose over the grams of your solution, where in this case, the mass of our solution is 375 grams plus X times 100%. And we know that our mass percent is equal to 2.75%. So now we just have an equation with a single variable and a single unknown, so we can solve for it procedurally. So we have 100 times X is equal to 2.75 times X plus 375. That gives us 100X is equal to 2.75X. And let me punch this into my calculator. Plus 1031.25. Okay. Moving this term containing X to the other side, we get 97.25X is equal to 1031.25. So then X is equal to 1031.25 over 97.25, which in turn gives us a value of X of 10.6 grams. So we need to dissolve 10.6 grams of sucrose. So once you set up the equation, it just turns into relatively straightforward algebra. Does this example make sense to everyone? Does this example make sense? Any questions? If not, let's test our understanding of this concept by trying to answer the following problem. So in this problem, we're asked how many grams of sodium chloride are present in 300 grams of a 5% mass over mass solution in water. So I'd like you to take about 3 to 4 minutes to work through this problem. If you have any questions, don't be shy to submit your questions or responses. Actually, before we do a problem solving session, let's do another example. This is another type of problem that you'll see for mass percent. And let's work this one through together, just to cover a broad swath of problems. So we're asked how many grams of sodium chloride are present in 300 grams of a 5% mass over mass solution. Okay, so we know this 5.0% is equal to the grams of sodium chloride over 300 grams of solution times 100%. So then the grams of sodium chloride are equal to 5.0% over 100 times 300 grams, which in turn gives us 15 grams of sodium chloride. So this is a nice simple problem where you're just solving for the mass of your solute using your mass percent formula. Any questions on this example? Any questions on this example? Okay, so now that we've covered two different types of mass percent problems, let's work on the following two examples, and you can submit your responses in the chat or via Canvas quiz 5.6.1. If you have any questions, really do not hesitate to ask. And I'd like you to work on these two mass percent problems. And we'll discuss these examples in about 6 to 7 minutes. And I'll be checking Canvas in the chat to provide feedback for these questions. And if there are any questions, or if you have a proposed solution for either of these two problems, don't be shy to share your proposed solution in the chat. So the responses I see in the chat look reasonable so far, and the responses I'm seeing in via Canvas look quite good. Spend another 5 to 6 minutes on this problem set, and let's try to get a few more responses via Canvas and in the chat, and we'll discuss momentarily. And the responses, so the response that I just saw in the chat I would double check to make sure that you accounted for the 100% in the mass percent formula. So let's try to get a few more responses for both of these questions. Thank you again for participating. We have almost the entirety of the class responding. Let's try to get a few more. And if you have any questions working through these problems, or if you're trying to check your work, don't be shy to submit your proposed responses. And we'll discuss in about another 2 to 3 minutes. So as almost the entire class has submitted a response and the responses look quite good, let's now look through these examples and let's discuss each of these problems in detail. So in the first case, we're asked how many grams of sodium hydroxide must be added to 250 grams of water to prepare a 3% mass over mass solution. Okay, so first and foremost, we know that the mass of solute we're going to represent as a variable x. The mass of our solvent is 250 grams. And the mass of our solution would be 250 grams plus x. Okay? So then our mass percent of sodium hydroxide, which is 3.00%, is equal to the mass of sodium hydroxide, x, over 300 grams plus x times 100%. Now we'll just execute on the algebra. So we have 3.00 times 300 grams plus x is equal to 100% times x. So 900 grams is equal to 97x. So then x is equal to 900 over 97, which in turn gives us whoops, let me just check the work really quickly. Oh, I don't know why I wrote 300. This is 250. I think I'm thinking of another problem variant that's popping up on the homework. So this should be 750 grams. Yep. So we have 750 over 97, which gives us a value of x of 7.73 grams of sodium hydroxide. There we go. And all the responses submitted in the chat and via Canvas for that problem look spot on. So let's look at the second. Any questions on this example? Any questions on this first example before we move on to the next? If not, let's look at this next problem. We're asked what mass of lithium carbonate is present in 150 grams of 2.5% mass over mass lithium carbonate in water, okay? So we know that the mass percent, one moment. So we know, oops. We know that the mass percent is equal to the mass of lithium carbonate over the total mass, which is 150 grams, times 100%. And we know that our mass percent is 2.5%. Solving for the grams of lithium carbonate, we have 2.5% over 100% times 150 grams, which in turn gives us 3.75 grams of lithium carbonate that we can round to 3.8 following sig fig rules. Any questions on this example? Any questions on this example? So if not, let's move on and let's discuss the next topic, which is volume over volume conversions. So percent by volume, very similar to mass percent, is defined as the volume of solute over the volume of solution times 100%. It can also be thought of, volume percent can also be thought of as the volume in milliliters of solute for every 100 milliliters of solution, where the volume of your solution is the volume of your solute plus the volume of your solvent. So let's look at an example. Let's look at an example, and we're asked to figure out how many milliliters of ethanol are needed to make 2.35 liters of a 25.6 volume over volume solution. Okay, so the volume percent is equal to the milliliters of ethanol over, and we have this volume in liters, so we're going to have to do a conversion. So we have 2.35 liters, and we know 1 milliliter, we have 10 to the negative third liter, which gives us 2,350 milliliters. You always want to make sure your units are the same. Times 100%. And we know our volume percent is 25.6%. So then, solving for the milliliters of ethanol, we get 25.6 over 100 times 2,350. And that in turn gives us our milliliters of ethanol of 601.6 that we round to 602 milliliters. So very similar to our mass percent problems that we've solved earlier. Does this make sense to everyone so far? Any questions so far? Okay, just to test everyone's comfort with this topic, let's work on the following example. You can submit your responses in the chat or via Canvas quiz 5.6.2. And I'd like you to calculate the milliliters of acetic acid that are needed to make 1.50 liters of a 6% volume over volume acetic acid solution. And we'll discuss this example in about 2 to 3 minutes, as it's a pretty fast calculation. And if you have any questions, don't be shy to unmute and ask your question verbally, to type your questions in the chat, however you want to communicate any questions that you have or communicate your solutions with the class. And we're already starting to see some responses in the chat for these questions. Let's try to get a few more responses and we'll discuss in about another minute to minute and a half. Okay, so let's discuss this example. So we know that our volume percent, which is 6.00%, is equal to the milliliters of acetic acid over the volume of the solution in milliliters. Let's convert liters to milliliters, and that gives us 1,500 milliliters times 100%. So then, solving for the milliliters of acetic acid, we get 6.00 over 100% times 1,500 milliliters, which gives us a volume, when we punch it into our calculator, of 6 times 1,500 over 100, which gives us 90 milliliters of acetic acid required. Does this example make sense to everyone so far? Any questions so far? Okay, so let's continue on and let's do another guided example. In this case, we're asked what volume of water is needed to prepare a 15% volume over volume solution of ethanol containing 5 milliliters of ethanol. So we know that the volume of our solute is 5.0 milliliters. The volume of our solvent is not known, so we'll write it as X. Okay, so we know that our volume percent, which is 15.0%, is equal to the volume of our solute over the volume of our solution, which we can get by adding our solute and solvent. Now that we have our equation in place, we're just solving it algebraically. So we have 15.0 times 5.0 plus X is equal to 500. X is equal to 500. 15X is equal to 500 minus 5 times 15. X is equal to 500 minus 5 times 15 over 15, and that in turn gives us 28.3. Whoops, let me just double check. Let me double check that really quickly. 5 times 100, 5 times 100 minus 5 times 15. Oops. Okay. Yep, and that gives us 28.3 milliliters of water. There we go. So it's very similar to our previous mass percent problems, except this time we're solving for the volume of our solvent. Does this make sense to everyone so far? Any questions on this example? Okay, so let's try to apply our understanding of this problem-solving manifold to the following problem. And you're welcome to submit your responses verbally via the chat or via Canvas Quiz 5.6.3 if you want to receive immediate feedback on this question. And we'll discuss this example in about 3 minutes. And if you have any questions at all, don't hesitate to ask them in the chat or to unmute and ask them verbally. Or if you have a proposed solution, don't be shy to share it in the chat or verbally. And wow, we already have some responses, but don't be shy to take your time and we'll discuss in about 2.5 minutes. And thank you for those who are responding in the chat and via Canvas. Let's try to get a few more responses. The responses I see look good so far, and we'll discuss in about another minute to minute and a half. Okay, so we have a reasonable sampling from the class. So let's now discuss this example. So we're asked what volume of water is needed to prepare a 10.6% volume over volume solution of acetone containing 10 milliliters of acetone. Okay, so in this schematic, we know that the volume of solute is equal to 10 milliliters. The volume of solvent is unknown, so we'll call that X. And the volume of our solution would be 10 milliliters plus X. So then we know that our volume percent, which is 10.6%, is equal to the volume of solute over the volume of our solution times 100%. Algebraically, we get 10.6 times 10 plus 10.6 times X is equal to 1,000. 10.6 times X is equal to 1,000 minus 10 times 10.6. And then X is equal to 1,000 minus 10 times 10.6 over 10.6. And that in turn gives us, when we enter it into our calculator, a value of X of 84.3 milliliters. So we need 84.3 milliliters of water to prepare this acetone solution. Does that make sense to everyone so far? Any questions on this example? Okay, so let's look at one last way of expressing concentration in terms of percent, and this is mass volume percent, which is grams per milliliter of solution. So mass volume percent is the mass of solute in grams over the volume of solution in milliliters. You can think of it as the grams of solute per 100 milliliters of solution. So to show how this works, let's look at an example talking about saline solutions, which are a 0.92% mass over volume solution in water. And we're asked how many grams of sodium chloride are required to prepare 35 milliliters of saline solution. So we know that the mass over volume percent is equal to 0.92 grams over 100 milliliters of solution. And that in turn, we'll just write this as 0.92 for now, percent, is equal to the grams of sodium chloride over 35.0 milliliters times 100%. Solving for the grams of sodium chloride, we get 0.92 gram per milliliter times 35 milliliters over 100. And that in turn gives us the following result. When we punch it into our calculator, 0.92 times 35 over 100, and that gives us 0.322 grams. Any questions on this example? Any questions on this example? If not, let's apply what we've learned to a new problem. And you're welcome to submit your responses in the chat, verbally, or via Canvas quiz 5.6.4. And let's try to answer the question. So sodium methoxide is sold often as 30% mass over volume solutions. And you're asked how many grams of sodium methoxide are required to prepare 250 mils of 30% mass over volume sodium methoxide solution. So we'll discuss this example in about 2 to 3 minutes. If there are any questions, don't be shy to ask. And don't be shy to submit your proposed responses via Canvas or in the chat, because it's really invaluable in helping me see any common errors or see how the class is progressing with the material. So we already have a fair number of reasonable responses, so we'll discuss in about another 30 seconds to a minute. And the responses I see in the chat look great so far. Okay, so let's discuss this example. So we know that our mass over volume percent is equal to 30.0%. That's equal to the grams of sodium methoxide over 250 milliliters of solution times 100%. Solving for the grams of methoxide, we get 30% over 100% times 250 milliliters, which if we punch it into our calculator, that gives us 75 grams. Any questions on this example? Any questions on this example? So we'll pause here for today and we'll resume the second half of our lecture in laboratory at 12:40. Yeah, so we'll resume the next part of this lecture at 12:40. And I will see you all in laboratory.